In this section, we'll talk about the way that sound is perceived and methods for protecting the ear from sound. Sound is actually compression and expansion of air, and it travels in waves. The length of a sound wave, or the amount of time it takes to go through a cycle of expansion and compression, is its wavelength. The number of waves that happen in 1 second is the sound's frequency. To our ears, frequency is pitch. Higher frequencies are higher notes, and lower frequencies are lower notes. How tall the wave is its amplitude, which to our ears is how loud the sound is. Most sounds we hear are a mix of frequencies, and the different frequencies that make up a different sound are its timbre. For example, how the same note sounds, Most sounds we hear are a mix of frequencies, and the different frequencies that make up a given sound are its timbre. For example, how the same note sounds different if it's played on a trumpet or on a flute. In both cases, the dominant frequency is the same, but the other frequencies that are mixed in give it its quality. The outer ear acts like a funnel that collects the pressure waves of sound and directs them inwards towards the eardrum or the tympanic membrane. The eardrum is just like a drum, and the pressure waves of sound move it in and out. As it moves, it causes the tiny little hammer, anvil, and stirrup of the middle ear to move. These transmit those sound vibrations into the inner ear to the cochlea. Because sound is a pressure wave, it works best if it's oriented towards the ear. Noise traveling away from the ear is harder to hear than noise traveling toward the ear. The cochlea is a long rolled up strip called the basilar membrane. It's covered with cilia and surrounded by fluid. As the cochlea vibrates, the vibrations propagate down that basilar membrane, moving those little hairs. As each hair moves, an electrical signal is generated in the nerve attached to it, just like in your skin. The brain processes these signals from the auditory nerves to interpret sound. Different sounds are associated with different parts of the basilar membrane. High-frequency sounds make it all the way down to the end of the membrane, so the nerves attached to those parts of the cochlea sense high-frequency sounds. Lower frequencies don't reach as far. Cochlear implants function by embedding tiny electrodes along the length of the basilar membrane. A microphone picks up sound and activates electrodes according to the frequencies that are picked up. The electrical signal from the implant replaces the signal that would be generated by cilia moving in the cochlea. When hearing deteriorates due to age or overexposure, the higher frequency parts tend to be lost first. In wearable systems, we're often concerned with protecting from sound. There are two ways to do this: by dampening it so that it doesn't reach the ear, or by masking it. Dampening is a mechanical process. A material like a compressible foam is used to absorb the pressure waves of sound so that they don't get to the ear. Masking is a little more complicated. To mask or cancel a sound wave opposite to the wave you're picking up needs to be created. That way, the compression and expansion of each wave cancels the other out. It's hard to do this perfectly in real time because the sound has to be sensed and then the masking sound has to be generated. It works best when the sound you're trying to cancel is pretty steady, like the hum of an airplane, or when you're just trying to get rid of certain frequencies, like a high-pitched whining. High frequencies are more easily masked than low frequencies.